Welcome to lecture 11 of electrical machines course. So in the last lecture, that is lecture number 10, we discussed about the equivalent circuit, how we can derive the equivalent circuit, exact equivalent circuit in fact. And from there we found the approximate equivalent circuit, right? And also I explained what is the importance of approximation, why we need the approximation so that the calculation will become easier. And also this approximate equivalent circuit is useful for determining the parameters of the transformer. In this lecture also we'll talk about that, how to determine the parameters like the resistances, reactances, and the magnetizing reactance and the core loss resistance, how we can determine these parameters experimentally. So it will be there in your lab also. You have to do it using the open circuit and short circuit tests. So it is there you have to do, but still theoretically a little bit we'll study here. And before that, let us see two more topics related to transformer. One is your voltage regulation, which is very important for a transformer. And also we'll talk about the maximum efficiency, the load at which we'll get the maximum efficiency of a transformer. Okay. So let us first talk about the voltage regulation. So what is in fact voltage regulation? Voltage regulation means suppose a device having some rated voltage, and if we are increasing the load and the voltage is decreasing, that means by that way we can find the voltage regulation by calculating the full load rated voltage minus the rated voltage minus the full load voltage, the voltage at the full load, by, or we can see here, by the full load voltage. Here we can see the voltage regulation is expressed in percentage, and it is nothing but the ratio of the difference between the secondary side voltage. This is V2 is nothing but this is the secondary side voltage at no load. That will give me the rated voltage minus the full load voltage at the secondary side, that is V2FL, divided by V2FL. V2FL is the full load secondary voltage into 100, right? So there are many other definitions also. There are many in other books also. Certainly this denominator is changed. Sometime it is used as V2 no load. Sometime it is used V2 full load. So here now we'll consider only V2 full load, not V2 no load. V2 no load also it is applicable and it is fine to use V2 no load. Okay. In some of the literatures it is there. They are using V2 no load, right? That is the rated voltage. So that is also fine. That will also give some result, and that these results will be approximately equal. So now we'll see the equivalent circuit of the transformer. You can see here this is equivalent circuit, approximate equivalent circuit, which is referred to the primary side, right? You can see here in the primary side the voltage is V1 and the current flowing through the core loss component is IC and magnetizing component IM, sum of which is the I phi, right? And I1 is the net current that is provided by the source, and IP is the current which is flowing into the load. The load and the parameters at the secondary side is referred to the primary side. That is nothing but already we discussed. RE1 is equal to R1 plus A square R2, right? And XC1 is equal to x1 plus a square x2. Already we know this, right? A square, a is nothing but n1 by n2. So similarly, load impedance is referred to this to the primary side, right? And so V2 dash also will be equal to a V2. Already we have seen this. Now for this particular circuit, how we'll find the voltage regulation? So for this circuit, under no load condition, what is the voltage? The voltage will be V1, obviously, right? If we will remove the load here, right? So the voltage that will appear across this will be V1 under no load condition, right? And under load condition, it will be AV2, that is V2 dash. V2 dash equal to AV2. So V1 minus AV2 by AV2, that will give me the voltage regulation into 100, right? Okay. Now similarly, if the equivalent circuit, if we can draw the equivalent circuit which is referred to the secondary side, we can see here in the secondary side the voltage remains as it is V2 ZL and RE2 XE2 RC2 XM2. These are all referred quantities, and V1 dash is also there right? V1 dash is nothing but it is equal to AV2, right? Okay, sorry, V1 by A. Okay, V1 by A. And RC2 is nothing but it is RC1 by A square. Already we have seen this. XM2 is XM1 by A square. Similarly, RE2 is nothing but equal to R1 by A square plus R2. And XC2 is nothing but X1 by, already we have seen this, just for your remembrance I'm doing this, right? Okay, so this is your equivalent circuit referred to the secondary side. And for this circuit, if we'll find the voltage regulation, it will obviously at no load condition, your voltage will be V1 by A, right? Across the load, the no load voltage will be, if the load is removed, then the voltage across these 2 points, suppose A and suppose this is marked as X and Y. So across X and Y, the no load voltage will be V1 by A. And under loaded condition, it is V2, right? So therefore, voltage regulation will be V1 by A minus V2 by V2 into 100, right? So this is the voltage regulation, how we calculate. And for both the equivalent circuit, one is when it is referred to the primary side, we have calculated. And when the equivalent circuit referred to the secondary side, we have also seen the equation for the voltage regulation. Now, if the quantities are given, now you can find the voltage regulation. Now, one such problem will do. So one transformer is given with the rating of 2.2 kVA. This is the kVA rating. This is the apparent power, right? Okay. So transformers are always expressed in the apparent power. The power rating is always in the apparent power because transformer is a static device and the voltage and current plays important role unless the load is connected, right? So therefore it is always expressed in the apparent power. So here the transformer is connected. The transformer rating is 2.2 kVA. And the voltage ratio is given, that is nominal voltage ratio 440 by 220. And the transformer is operating at 50 Hertz. It is a step down transformer and it has following parameters. And the parameters are referred to the primary side. So RE1 is 3 ohm, XE1 is 4 ohm, RC1 is 2.5 kilo ohm, XM1 is 2 kilo ohm, right? So now the transformer is operating at full load with a power factor of 0.707, lagging, right? So this power factor we should remember, this is lagging power factor with a value of 0.707. And we need to determine the efficiency and the voltage regulation of the transformer. So we know the voltage regulation formula, the efficiency formula, everything, right? So we need to find, so in order to calculate the efficiency, we must know power out and power in into 100, right? So in order to find the power out, I must know the voltage, right? And this circuit is given, which is referred to the primary side, right? So therefore, your output voltage, I can write it as AV2 into IP, and power factor angle is cos theta. That will give me the PO, right? And similarly, P in, if I want to find P in is nothing but PO plus the losses, right? So the losses, how I'll find the losses? One is your magnetic loss, right? That is the core loss, we can say, right? So core loss plus your copper loss. You can write it as PM, magnetic loss, PO plus PM plus PCU, copper loss, right? Plus, sorry, this is your P in and 200, right? Or else in other way you can find it P in by what? In other way you can find V1 I1 cos of theta 1, right? This is theta 2. This is load power factor and this is theta 1, right? So this is the way we can calculate. So if we know this angle of current I1, then I can easily find V1 I1 cos theta, right? Theta 1. Already you have done this. And voltage regulation for this circuit, we know this is the no load voltage is V1 minus AV2 by AV2 into 100, right? So this will give me percentage voltage regulation. This is percentage efficiency. So now I can find it, right? So then we can proceed. You can see the problem. This is your equivalent circuit and the parameters are referred to the primary side as given. So RE1 is given, XE1 is given, right? And the load power factor is given, and 2 kilo ohm is your XM1 and RC1 is 2.5 kilo ohm. So now we can find here. First let us find the transformation ratio, that is A. A is nothing but 440 by 220, that is equal to 2, right? And V2 is given, that is 220 volt here, okay? So now your AC is 2200 VA, that is 2.2 kVA. And I2 I can find from this, like just by dividing V2 2200 by 220, that will give me 10 ampere. So now we know the lag power factor is lagging, so I can find theta. Theta is cos inverse of 0.707 and it is lagging, therefore minus 45 degree, right? Minus of cos inverse 0.707. And so using the load voltage as reference, if we'll consider the load voltage as reference, the I2 will be having magnitude 10 ampere and current will be minus 45 degree because it is lagging, right? Lagging the voltage. So now I can find IP. IP is nothing but I2 by A. So it will be I2 by A is equal to 2. So that will give me 5 angle minus 45 degree. And then I can find V2 dash, that is AV2, that will give me 440 0 degree. So here AV2 is 440 0 degree. Now I can find V1, right? So your V1 will be V2 dash plus IP into RE1 plus JXE1, right? So just by substituting the values, you will get 464.762. Angle is 0.44 degree. So now after finding V1 from the circuit, so if you find V1, then you can find IC and IM, because IC is nothing but V1 by RC1 and IM is nothing but V1 by JXM1, right? So now similarly I can find proceed IC equal to V1 by RC1, right? And this is your V1 by JXM1. So that will give me 0.186 ampere, very less current, 0.44 degree, and IM is 0.232 minus 89.56, right? So now I can find I1 because I1 is summation of IP plus IC plus IM. If we'll go to the figure back, so I1 is equal to I5 plus IP, I5 equal to IC plus IM, right? So therefore I1 equal to IC plus IM plus IP, right? So that is what we can do here. And after finding I1, I can find both the power output and power input. So power output is nothing but real part of this, right? So just by finding the real part of this, uh, this is nothing but I2 star, right? Okay, or IP star, you can say IP star, right? So therefore the minus 45-degree angle became plus 45-degree, right? So similarly here also the current I1 has a lagging power factor minus 45.33. Here it is mentioned positive means it is I1 star, because we know complex power is VI star, right? So therefore real part of this will give me the real power, right? So similar real power output is real part of this, and a real active power input power will be real part of this. So that will give me these values, and then I can find the efficiency, right? So efficiency is coming around 90.6%. Similarly, I can find the voltage regulation. So for voltage regulation, I know AV2 is 440 and V1 is 464.762 at full load condition. So now I just by substituting these values, I can find the voltage regulation is coming around 5.63%. So that means if your voltage regulation is less, your transformer is performing better always, right? So therefore the voltage regulation value should be lesser and lesser. That means if your voltage regulation is 0, that means your transformer is perfect. That means it is an ideal transformer, right? So if your voltage regulation is more, it is increasing, that means your transformer's performance is less. Okay. Okay. So now coming to the another topic, that is maximum efficiency criterion. What it means at what load of a transformer, that means suppose a transformer is there, right? Suppose a transformer is there and we have input and output. So efficiency we know is output by input, and obviously input output they depend upon the current, that is the load current, right? So these two factors depend upon the load current, and so we need to find the load current at which the efficiency becomes maximum. That means your transformer, the performance of the transformer in terms of the efficiency is highest. Okay, so it will give the maximum efficiency. Okay, so how to find that? So let us write the equation for the efficiency. Then we know the criteria of if we'll write the equation of efficiency in terms of current, and we know the criteria of maximum to get the maximum point, right? So that means if I'll take the derivative of efficiency with respect to the current and equate to 0, and from this equation whatever current I will find, that will give me the current or the load current at which we get the maximum efficiency, right? So let us see, then we'll proceed. So we know in the transformer we have different types of losses, and when we give the input, that is V1, I1, let us say from the primary side, right? And this input in fact converted into three parts. One is two component losses, and another component is your output, right? That is in fact provided to the load. So now this is in fact useful, and other two components are losses that in fact goes out in terms of heat, right? So PM indicates the magnetic loss, okay, magnetic loss, and your PCU indicates the copper loss. So these are the two components. Now this magnetic loss, we know this will remain constant till the voltage and frequency remains constant. Unless there is a change in the voltage and frequency, this remains constant. We have already seen the equation for hysteresis loss and eddy current loss, right? So they are all dependent upon the voltage and frequency, right? Already we have seen this. So therefore, unless unless there is a change in the voltage magnitude and frequency, there is no change in the magnetic loss. It will remain constant at no load also till full load. It will remain constant. But the copper loss, if we'll see, it is a function of I square, right? I2 square. If you'll see the copper loss, it is directly proportional to I2 square. That means as your load is varying, it is proportionate, not proportional, it is varying in the term of square, right? So if we'll make a function of copper loss PCU versus load current, it will look like this, right? Okay. So it is a square function. So now if we'll find the copper loss equation, how it looks like, just a minute. So your copper loss is, let us, so your copper loss is IP square RE1, right? So if we are finding it in the equivalent circuit form, which is referred to the primary side, then your copper loss will be nothing but IP square RE1. And your, if we'll write the P in input power to the transformer, that is the output power plus magnetic loss plus copper loss, right? So that means your output power is AV to IP cos theta plus PM is your magnetic loss plus IP square RE1 is your copper loss, right? So now if we'll write the expression for efficiency, equation for efficiency, it will be output by input. So that will give me AV to IP cos theta divided by AV to IP cos theta plus PM. PM is your magnetic loss plus IP square RE1. So we are calculating this efficiency considering the circuit is referred to the primary side, because we are considering RE1 here and IP as the load current, right? So IP square RE1. Now how to find the maximum efficiency condition? That is, if we'll take the derivative delta eta upon delta IP, delta IP equal to 0. Just by taking the derivative, you will find easily that, just do it in your home. You can find the same expression like we are getting here. The expression will be this. So your IP square RE1 will be equal to IPM. So, okay. So here the IP is represented as IP eta because this condition is for maximum efficiency. So therefore IP eta square RE1 equal to PM. So this condition we'll find after taking the derivative and equating to 0. That is delta eta upon delta IP will be equal to 0. Just do this, we'll find this equation, right, by equating to 0. And then from this expression, we can see that because the copper loss is becoming equal to the magnetic loss or core loss, right? So that means what your maximum efficiency criterion says, that when the copper loss becomes equal to the core loss, that means if we'll vary the load, so the load point at which the copper loss becomes equal to the core loss or the magnetic loss, at that point we can say that we'll achieve the maximum efficiency. So if we'll vary the load, here we can see the percentage load is varied, right? And here the power loss is drawn. So your core loss remains constant throughout. This is your core loss curve. And if we'll plot the copper loss with respect to the load, it will be exponent. It is in terms of square. It's the varying like square, right? Square function. So now if we'll see at a certain point, the core loss and copper loss characteristic will cross each other. That intersection point will give me that intersection point. In fact, if we'll vertically put there, this load will give me the load point at which we'll get the maximum efficiency. That means the point at which your core loss is becoming equal to the copper loss. Okay, so this is the load at which we get the maximum efficiency. Okay, so now let us calculate the maximum power output. So now just little bit modifying this. So if I'll just find out IP eta, that is the current here, that I can find I PM by RE1 square root, and again multiplying the full load current in the numerator and denominator, I'll see is multiplying the square of full load current in the numerator and denominator. If we'll take the full load current outside of the square root, it will become IPFL into square root PM by IPFL square RE1. So what this indicates, this is nothing but your copper loss at the full load condition, right? Copper loss at full load. Okay. So that means this indicates a fraction. Okay. And IP eta is the load current at which we get the maximum efficiency, right? So that means your current at which you want to find the maximum efficiency. So that current we can find just by multiplying the full load current with this fraction. That fraction is nothing but it is the square root of PM by IPFL square RE1. That means core loss by copper loss, right? At full load condition. That means the square root of core loss by copper loss under full load condition, at full load condition, right, gives me the fraction of the full load at which we'll get the maximum efficiency, right? Okay, so now if we'll see this IP eta is becomes equal to IPFL square root PM by PCUFL. PCUFL is nothing but copper loss under full load condition, and PM is your magnetic loss, which remains constant throughout. As I told, it remains constant from no load to the full load, right? There is no variation. Only copper loss will vary. Therefore, this copper loss is at full load condition. Okay. Now we can find the VA maximum efficiency. That means the volt ampere or the apparent power output of the transformer at maximum efficiency will be nothing but VA rated, because just multiply here V2 or AV2. You can multiply AV2 both the side of the transfer, both the side of this equation, right? So now it will become VA at the maximum efficiency equal to VA. This is your rated VA, rated kVA or rated VA, right? Apparent power at the rated full load condition. This is your apparent power at the maximum efficiency multiplied by magnetic loss divided by full load copper loss square root. Okay, so this is how we find the volt ampere, the apparent power under the maximum efficiency condition, right? Okay, now let us do a small problem in order to illustrate this concept of maximum efficiency. How to get the maximum efficiency, the load point at which we get the maximum efficiency. Suppose a transformer is given here, the rating is 120 kVA and the ratio, voltage ratio is given 2400 by 240 volt, right? And step down, it is a step down transformer. And the parameters as follows. R1 is given 0.75 ohm, X1 is 0.8 ohm, R2 is 0.01 ohm, X2 is 0.02 ohm. The transformer is designed to operate at maximum efficiency at 70% of its rated load. Okay, so it will give the maximum efficiency at which load? It is the 70% of its rated load, right? Okay, and under what condition? The power factor, when the power factor is 0.8 power factor lagging, right? Now we have to determine the kVA rating of the transformer at maximum efficiency, that is BA max, right? Maximum efficiency. and B is the maximum efficiency. We need to find the maximum efficiency, the efficiency at full load and 0.8 power factor lagging, so that we can compare these efficiencies, right? What is the maximum efficiency we are getting and the efficiency at full load, whether they're equal or they're different, and the equivalent core loss resistance. So we need to find RC1, right? Okay. So let us proceed then. So this is your equivalent circuit referred to the primary side, right? And so then we can find IP first. So IP will be nothing but your S by V, right? S by V2 or AV2 you can say. So AV2 is nothing but your 2400, that is if we'll multiply 2400 divide 120 kVA by 2400, then we'll find 50 ampere. IP is 50 ampere, right? Okay. So now your your load at which the maximum efficiency occurs is 70%. So therefore I can write IP eta is equal to 0.7 IP, right? And that is equal to 0.7 into 50 ampere. That will give me 35 ampere. Then the first question is kVA rating at maximum efficiency. So the current I know, the voltage I know, so I can multiply it and divide by 1000. That will give me the kVA at maximum efficiency. That is 35 ampere at the maximum efficiency, the load current into 2400. This is the load voltage, right? AV2 divided by 1000, that gave me 84 kVA, right? Okay. So this is your 35 is your IP eta, and this is your AV2, right, by 1000. Similarly, your copper loss under this condition, that will give me this maximum efficiency condition will give me I square into this IP eta, right? IP eta square into R1 plus A square R2. A is 10, right? 2400 by 240, that is 10. So 35 square multiplied by 0.75 plus 10 square into 0.01, that gives me. So under maximum efficiency condition, your copper loss is equal to the magnetic loss. So I can write here copper loss is equal to the magnetic loss. So therefore it is mentioned here PM equal to PCU eta, that is equal to 2143.75 watt. Okay. So now we need to find the maximum efficiency. So maximum efficiency is nothing but it is P out by P in. We have to calculate under maximum efficiency condition. So for calculating the P out, we know this, and we need to multiply the power factor, right? So let us see here. So here PO is 2400 into 35 into 0.8. 0.8 lagging power factor is given, that is PO. And P in under this condition, maximum efficiency condition, where PM is equal to PCU eta, that will give me 71,487.5 watt. Okay. So now if we'll find the maximum efficiency, this is eta max. Maximum efficiency will be equal to P out by P in. So if we'll divide, it is giving 94%. Okay. Now we need to find the efficiency at the full load condition. Under full load condition, if we'll find the efficiency under full load condition, right? So we need to find PO and Pin. So PO is 2400 into 50. 50 is your full load current into 0.8. So that is giving you 96,000 watt. And copper loss will be around 4,375 watt. Here we are substituting the full load current. Then just substituting the values in the efficiency expression. So this is P out by P out plus magnetic loss plus copper loss, right? This is your magnetic loss, this is your copper loss. Because magnetic loss is equal to the copper loss under maximum efficiency condition. So that will remain same. So therefore it is remaining same, 4,000. Sorry, this is your copper loss. Sorry, this is your copper loss. This is your magnetic loss. So this is remaining equal to this, right? Okay. So now if we'll find the efficiency at full load, we are finding 93.6%. Okay, it is very near to a maximum efficiency, right? So uh, still there is a difference, right? So maximum efficiency is 94% and the efficiency at full load is your 93.6%. Now you can find RC1 very easily. RC1, very easily we can find this. RC1 is nothing but, what is this? VOC or V1, you can say V1 by IC, right? The current passing through the core loss resistance, right? And I can write this as V1 square. Okay, so V1 square by POC. That is the sorry, this is PC. PC is your core loss or magnetic loss component, right? So PC is nothing but this is 2143.75. Just by substituting the values, I'll get RC1 as 2686.88 ohm, right? Okay. Okay, so up to this we have covered the voltage regulation and then your the criterion for maximum efficiency. Now let us talk about the determination of the transformer parameters. So how we can determine, suppose a transformer is given to you. Now the question is how to find the parameters in the transformer. The parameters means the equivalent circuit parameters, right? So how to find this? So the equivalent circuit parameters of a transformer can be determined by performing two tests. One is your open circuit test and other one is the short circuit test. So these both tests need to be done when we need to find the parameters of the equivalent circuit representation, right? And this you will also do practical in your lab. Okay, so before that, let us see the open circuit test, how to proceed, and then we'll see the short circuit test. So okay, so for open circuit test we need these equipments first. So we need one ammeter and we need one voltmeter. You will see these equipments in your machine lab, it is there available, and then one wattmeter we need. So wattmeter, what it does, the function of the wattmeter is to measure power, to measure real power. That means active power, not the reactive power or apparent power. It only measures real power in watt, kilowatt, or whatever, right? Only in watt. Okay. And current, the ammeter measures current in ampere, and voltmeter measures voltage in voltage, right? So volt. Okay. So now, so how to proceed then? So the procedure is here. The procedure is we need to keep the high voltage side open circuit. Therefore, it is called open circuit test. And we need to feed the rated voltage from the low voltage side of the transformer. Obviously, we know there are two windings in the transformer, right? One is your high voltage winding. This is low voltage, high voltage winding and low voltage winding, right? So here we are not concerned about primary and secondary, because when a transformer is given to us, it will have a single phase transformer I'm talking. So in a single phase transformer, we'll have four terminals. One terminal at the low voltage side, sorry, two terminals at the low voltage side, and other two terminal at the high voltage side. Now it is our requirement. Based on our requirement, we can make one side primary and other side secondary. So primary side will make it when we'll connect it with source, and secondary side will make it when we'll connect one side to the load, right? Your high voltage side can become primary, low voltage side can become primary, or high voltage side can become secondary and low voltage side can become secondary, right? It is based upon our requirement and connection. Okay. So now under this situation for the open circuit test, we are connecting all the equipment at the low voltage side and feeding the rated voltage at the low voltage side, and we are keeping the high voltage side open circuit. Why don't we choose the high voltage side to connect the equipments and the feed the voltage source? So there is a reason behind this, because the high voltage side, certainly if the high voltage side will take, we need the equipment more sophisticated, and we need to, because the equipments are not generally designed for high voltage circuit, they're for low voltage circuit, right? So therefore high voltage side is not chosen for the experimental purpose, it is kept open, right? Okay. And if we'll choose the low voltage side, we can easily feed the rated voltage. From the laboratory side, we can feed the rated voltage, and we can also do the experiment by putting the low voltage equipments. So that is safety to the personnel as well, and it is also, it can be performed in the laboratory as well. So therefore, it is important to choose always the low voltage side for connecting the equipments and feeding the rated voltage. Okay, so therefore high voltage side is kept open. So now under this condition, if we'll make the equivalent circuit of this transformer, how it will look like? So if we'll make the equivalent circuit, then under this condition your secondary side is open, so therefore this will be open terminal, and only in the primary side we are feeding the voltage source, rated voltage, right? Now this current is 0. This is IP or whatever we call it. Let us say I LP, sorry, ILP. Okay, so that will be 0, and IOC will only flow, that is the open circuit current, and that current will be only, it is providing to the core loss component, and it is providing to the magnetizing component, right? That means IC and IM. That means I can say that IOC is nothing but is equal to IC plus IM, right? Okay, so now whatever equipment we have connected, suppose ammeter, this ammeter will read, suppose this ammeter will read only IOC, that is the open circuit current, right? So that means when we'll take the reading from the ammeter under this condition, giving the rated voltage, this side is open, so this ammeter will give what? This ammeter reading will give only IOC, right? So ammeter will read only IOC. And similarly, your, if you have connected a voltmeter here, you have connected here a voltmeter. So this voltmeter will give me what? This will give me open circuit voltage, VOC, right? And similarly, the wattmeter, what it will give? The wattmeter is here, right? So the wattmeter will give me, that is POC. Okay. So this POC is nothing but the loss in this resistance, RCL, right? Okay. So this POC is nothing but I can write it as VOC into IC. This is equal to POC. IC, not IOC. So IOC is equal to IC plus IM. They are also vector sum, right? They are not the direct sum. Okay. So now let us proceed with the phasor diagram. So let us see the phasor diagram here mentioned. Phasor diagram, what it shows that your VOC is taken as reference, and obviously IC will be in reference to VOC. Okay. And your IM obviously will lag by 90 degree to VOC because it is completely inductive circuit, right? So your IM will lag VOC by 90 degree. And the sum of IC plus IM will give us IOC. That is the vector sum of IC plus IM. That will give me IOC, right? Okay. So now if we'll find the, under this condition, the apparent power SOC, that is nothing but will be equal to VOC into IOC. Okay. Now I can find the power factor angle phi OC. So phi OC will be nothing but equal to cos inverse of POC SOC, because I know these quantities VOC and IOC from the measurement, right? IOC and VOC, and I can find SOC, and I know POC from wattmeter reading, right? POC is known, VOC, IOC is known, therefore I can calculate SOC. So therefore I can calculate phi OC, that is the angle between IC and IOC, or VOC and IOC. That means IOC is lagging by phi OC. So phi OC is nothing but is equal to cos inverse of POC by SOC. Okay. Obviously, because POC will be in this direction and your SOC will be in this direction. So therefore, phi OC will be cos inverse of POC by SOC. And from this, your IC will be, obviously IC will be IOC cos phi OC, and IM will be equal to IOC sin phi OC from this phasor diagram, right? So it is obvious. So now I can find your RCL. So from this, the objective of this part of the experiment or open circuit test is to find these two parameters. One is RCL and other one is your XML. So I can find RCL by just dividing IC with VOC. So VOC by IC will give me RCL. So therefore IC is nothing but IC is what? IC is nothing but I can write it as POC by VOC. Okay, so I have already told POC is nothing but is equal to VOC IC, right? So therefore I can write IC equal to POC by VOC. Just substituting this in IOC, I will find VOC square by POC. So what is the purpose of converting this into power form? Because POC I am directly measuring from the wattmeter, right? POC is known to me, and VOC is also known to me by this measurement voltage. So therefore directly I can find RCL, that is equal to VOC square by POC. Okay, so that will give me directly the value of RCL. Now similarly I can find XML, that is the magnetizing reactance, right? Similarly I can write XML is equal to VOC by IM, and IM I can write it as QOC or else I can take IM directly from here, or I can convert this IM in the form of reactive power. So that is IM is nothing but will be equal to QOC QOC upon VOC. Okay, so that will give me, if we'll substitute this here, then it will give me VOC square by QOC. And QOC I know QOC is SOC square by POC square. So rather than doing this, I can directly substitute IM from here, because IM I know IM is equal to IOC sin phi OC. So I'll substitute here IM, I can find directly XML. No need to find this, even if you can go further to calculate QOC if it is required. Okay. So this is how here using the open circuit test we found the parallel branch parameters, that is RCL and XML, that is the core loss component resistance and your magnetizing branch component, that is XML. So both of these we found. Now we'll go for how to find the series components, that is RE, RE1 and XE1, right? So we have two more components here, REL, XEL, right? So we need to find this. So then we'll do the short circuit test. So again in the short circuit test we'll use again these three devices, three equipments. One is your ammeter, voltmeter and wattmeter. Now the question is how, in which side these equipment should be connected and which side it should not be connected. Okay, so when we connect it as at the high voltage side, it is safe, because under short circuit case, short circuit condition, here we need to inject very low voltage. So this is your variac auto transformer through which we can vary the voltage, right, gradually. So this is your auto transformer. Huh? You will see it in the lab. What is auto transformer? A variac. We call it variac. Okay. So so in the short circuit test, what we do, the procedure is like for the low voltage side is shorted, okay, and in the high voltage side, we increase the voltage gradually from 0 up to this ammeter reads the rated current at the high voltage side. Okay, that means high voltage side current it rates rated high voltage current. Up to that point, this voltage will be increased. So that means this voltage, how much we should increase this voltage so that it will give the net short circuit current. So it will be very less voltage. It is around 6 to 10%, 6 to 12% sometime, right? So why it is very small voltage we need to inject in order to have a short circuit current in high voltage side and low voltage side as well. How it is? Because if we'll see this, if we'll make it short circuit, your V2 became 0, right? Completely. Now whatever the voltage induced across this E2 will be very less in order to provide the circulating current here, the short circuit current, right? Okay, so because we know E2 is nothing but equal to V2 plus I2, I2 Z2, right? So we know this V2, when V2 becomes 0, then E2 is nothing but is equal to I2 Z2. And Z2 is very small parameter, right? So that will give me very less value of E2. And that will reflect here as E1. So E1 will be very less, and therefore your voltage here will be very less. It will be approximately equal to E1. So therefore your voltage across this will be the voltage requirement for circulating the rated current will be very less, right? So now under this condition, if we'll draw the equivalent circuit of the transformer, how it will look like. So the equivalent circuit will look like this. REH, JEH will be in series, and the secondary side is short circuited. This circuit is referred to the high voltage side because all the experiments we are doing in the high voltage side. In the open circuit case, we are doing all the experiment in the low voltage side. Therefore, the circuit is referred to the low voltage side, right? Here, therefore, here the short circuit test we are doing at the high voltage side and the low voltage side is shorted. Therefore, your equivalent circuit will be referred to the high voltage side. Remember this, this equivalent circuit is referred to the high voltage side. So the equivalent circuit will be only having the component REH and JXEH. Now the question is, where is that parallel branch that represents the core loss component and the magnetizing component? Sorry, this will be inductance. So where is that component? So this will be RCH and XMH. So where does these components come? Because these components will be neglected here because when we're injecting a very reduced voltage and these values are in fact very high, right? And therefore when we are giving a low voltage here at this side, then obviously the current drawn by this parallel branch will be very less. That means your core loss plus Im, that will be very less as compared to the net current or net short circuit current or full load current. This short circuit current is nothing but full load current, right? It will be very less. Okay. So therefore, this component is neglected, right? So therefore, this is neglected, and only component we're considering here is REH and XEH. Okay. So now, through the measurement, we found here the current by ammeter, voltage using voltmeter, then power here wattmeter, right? Now We know the current flowing here, ISC, through this ammeter, right? And through the voltmeter, I know VSC and short circuit voltage. Then through wattmeter, I found the power. Okay, power drawn by the circuit PSC. So what are the components are there in this circuit? Only REH and XEH. So whatever this wattmeter will show, this power loss or power component PSC, it is nothing but only this power is lost in this resistance, this equivalent resistance, right? So therefore PSC I can write it as ISC square into REH, right? That is equal to ISC square into REH, right? Now from this I can find REH very easily. REH is nothing but PSC by ISC square. So PSC I know from wattmeter reading and ISC I know from ammeter reading. Just by substituting I'll find REH. And similarly XCH, how to find XCH? So if you'll find JDH, JDH is nothing but VSC by ISC, right? The voltage across this and current flowing through the circuit. If we'll divide it, it will give JDH. Now XCH will be JDH square minus REH square root, right? So that will give me XCH. Okay, so that is your reactance, right? So now we found the reactance and the resistance, series reactance and series resistance. Whatever, if you'll find it in the high voltage circuit, you can refer it to low voltage circuit just by multiplying the factor of a square or 1 by a square, right? Whatever is requirement. So here if we'll uh, refer to the low voltage side, it will be divided by a square, right? So now this is what I told. Okay, so REH is nothing but PSC by ISC square, and your JDH is nothing but equal to VSC by ISC. XCH I can find JDH square minus REH square root. And obviously again, if we found the equivalent parameters. Now the question is how to find the exact parameters like R1 or RL, RH and XL and XH. How to find this? So it is said in the literature that for an optimal design of transformer, the copper loss in the high voltage winding is equal to the copper loss in the low voltage winding, right? So for the optimal design of the transformer, this criteria should be fulfilled. That means whatever the copper loss in the high voltage winding should be equal to the copper loss in the low voltage winding. And from this expression, we can find further this, we can segregate this REH and XCH to RL and RH, XL and XH. So we'll see it in the next class because time is over now. So we'll continue in the next class and we'll do a small problem also with this. Okay, so thank you very much for your kind attention. Thanks a lot.